We are really going to cover the Bernoulli or the Archimedes principle before we get to the Bernoulli equation today. One thing I wanted to do before we ever get started, well, with that stuff, is the demonstration that I wanted to do last class 3, but forgot to have out here. So this here is actually real simple. I have a piece of rubber. It's about 8 inches square with a handle on it because we physicists are that way. And I put it on this, and I pick up the metal real easy. And in fact, Brandy, since you're the closest, why don't you come up here and help me? What I'm going to do is I'm going to hold this plate down and have Brandy try to lift up straight up on that. Right? It's not going to happen, she says. So I have a clicker question right now that is, why is that thing held down? Why didn't it just come up when she tried to lift it up? So here's our clicker question that's available to you now. What holds a suction cup to an object? Now, we haven't talked about it yet, so this is asking you to try to take what you know and apply it to something that we haven't discussed, and then we'll discuss it. Oh no. So I'll give it about 5 more seconds. You had time to read it there, Jonathan? Okay. All right, and our breakdown is 15, 12, 7, 11, and 2. So we can see we're all over the board, which is fine because, like I said, we haven't discussed this yet. We've talked about some general principles. So let's look at this. If I want to talk about why these two things are held together, I'm going to start by saying, well, let me look at one object. Which object would be the obvious one for me to check into? The suction cup, as we like to call it. So I'm going to make the suction cup my object I look at. So here's my suction cup. Obviously, if it sticks together, its forces are holding it together somehow. So I'm going to do something with forces. So right off the bat, I'm going to make a free body diagram. What forces are acting on this suction cup as I hold it here? Gravity. Okay, there's gravity. So there's a force of gravity equal to the mass of the suction cup times gravity. Okay, there is a normal force when it's sitting here, but when I lift it up, remember what direction is the normal force? Pushing out, or in this case, it actually doesn't have a normal force, but it does have a force on the bottom side and another force on the top side. These are two forces that we've ignored until this chapter. Okay, there's a force due to air pressure. So on top, I'm going to call it force top. It's going into the surface, and it's going to be the atmospheric pressure times the area. What about on the bottom side? Not actually the buoyant force. It's similar in concept, but not the same. It's just going to be, again, the force due to air pressure in the bottom. So those are the forces that I have acting on it. So if I take Newton's second law, define up as y, sum of the force in the y direction is equal to mass times acceleration in the y direction. If I'm just holding it stationary, the acceleration is 0. So looking at my picture, that's going to be the force in the bottom minus the force in the top minus the force of gravity equals 0. somehow the force bottom minus force top needs to equal the force of gravity. How can that work out? What force is pushing on the bottom? I swear I have a sign error. Can somebody see a sign error I made? Top of the, let's do it down. That one's up. Should be right. Still feels like a sign error. How is this possible? Well, let's make one more substitution. Force of the bottom was pressure bottom times area. Force in the top was pressure atmosphere times area. So I factored out the atmosphere. So what I have to have is a difference in pressure between the bottom and the top. The pressure on bottom is going to have to be different. How does the pressure on bottom become different? When I pick this up, notice if I take it sideways, I can lift it right off. It's not a problem at all. But when I lift it up, it's sealed along the edges so no air can come in. It starts with the pressure of an atmosphere of pressure underneath. But as soon as I try to lift it, because it's sealed, no air comes in, the rubber is flexible, it comes up. But what happened to the volume of the air when I lifted it up and the rubber comes up? The volume had to increase. But if the number of molecules didn't change and the volume increases, then the pressure has to decrease. So the pressure underneath decreased. So the pressure on the bottom is a lower value than the pressure on the top. And now we see why I believe I have a sign error, because pressure bottom is smaller, pressure atmosphere is larger. That's a negative on the left-hand side, positive on the right-hand side. For the life of me, I can't see where I would have made a sign error here.
But you're treating force gravity as negative. So,
well, its direction is down. Oh, I know what I'm doing wrong. It's holding this up. That's what I'm forgetting. So I'm actually missing a force. I'm missing the force of that there, the metal plate pulling down on it, because it is holding the metal plate up. So now it's bad to make a mistake, but it's worse if you never figure it out. The force of the plate is downward. There's where I made my mistake. Well, actually, that's force acting on pulling down. Okay, I'm feeling really non-confident.
You're applying a force to it when you're holding it up.
True. Wow. It's true. I should have done the free body diagram before. Because this force bottom is actually what is then holding up the plate. So it should have been force applied. There we go. So we'll leave it like that. The key is the pressure underneath has become lower. And because it has a lower pressure underneath, there is a net force due to pressure. And that net force can actually be really large. Atmospheric pressure, about 14.7 pounds per square inch. That thing's about 8 inches square, so I'd like to approximate that as approximately 15 pounds per square inch of pressure and 60 square inches. Instead of 64. Because then I can do it in my head. And that's a total of 900 pounds that air pressure is pushing down on the top of that. Now, remember last class where I talked about my hand and the air pressure pushes down with a pretty big force. Normally, I have that same 900 pounds pushing up. But as soon as I start to lift, the pressure underneath gets smaller. And because it's smaller, let's say it goes down to 10 pounds per square inch. Then the upward force would only be 600 pounds. And I'd have a total of 300 pounds of net force between the air pushing down and the air pushing up. So that's how a suction cup works. So now that I've gone through this, let's look at the answers. The negative absolute pressure between the suction cup and the object. This one was incorrect because pressure can only be positive or zero. You cannot have a negative absolute pressure. So negative absolute pressure doesn't exist. Why? Because pressure is always caused by something pushing into the surface. If you have nothing pushing into the surface, then it's just zero pressure. You would have to actually use glue or an adhesive to pull the other direction. Okay, the second one, the negative gauge pressure. What is the gauge pressure? Okay, it's the pressure minus a reference, which is usually the atmospheric pressure. So did it have a negative gauge pressure when I was in this situation? Yes, because the pressure was less than atmosphere, still bigger than zero, but a negative gauge pressure. So this one here would almost be right. What direction is the force caused by that air pressure underneath? It's pushing up on the suction cup. The thing that holds the suction cup to the metal then is the atmospheric pressure pushing on the suction cup. That's what pushes the suction cup to an object. That's bigger than the force pushing it away, and that's why it sticks. Adhesion and cohesion are not parts of this problem. I put those words in because we're going to talk about capillarity, hopefully, today. And adhesion and cohesion are important words when we talk about capillarity. All right, that was our little sidetrack before we get into the buoyant force and actually Archimedes' principle. So you remember the whole story about Archimedes, Eureka. Well, the buoyant force is a big part of the end result of that. So this picture here shows a piece of water missing, or a piece of water not missing. But we could imagine this is made of anything we want. You know, maybe that's a piece of metal. In lab today, no, not today, tomorrow. By the way, this reminds me, we'll definitely meet here for lab tomorrow. I will not be able to have my office hours today because we're going to be trying to see if it's possible to teach class from the ill-equipped classroom up in Dick Building. And so we may meet there on Wednesday, so I'll let you know in lab tomorrow. It's because we're having some audio problems and they've never hooked up the second monitor over there in Southwestern. So to try to get these things going, we're going to see if we can do it up there. Just so I won't be in my office for the office hours today. I want to make sure that's clear. Okay, so we have this object here, and what I'm going to do is two things. Number one, I'm going to calculate the weight of this object, and number two, I'm going to calculate the buoyant force. So the buoyant force, by its very definition, is the net force caused by the fluid pressure on my object. So if I look at this object, I would have forces on the sides. And notice I made my arrows so they're shorter down at the bottom, or shorter at the top, longer at the bottom. Why? Because the pressure is increasing as you go down. On the top, I'm going to have the forces down. On the bottom, the forces up. That picture does not look the same as the free body diagram to the right. What's different about it? There are two things that are different. What's the first and most obvious difference you see? The horizontal forces. The textbook did not put the horizontal forces on because if you look at them, these two are in the opposite direction, but of the same magnitude, so they add up to zero. And for every height, as you go down, you'll have something on the other side so that it adds up to zero horizontally. And it doesn't matter what shape it is. If it's cylinder, it's really easy to see that it's going to add up. But any random shape, you're still going to have the horizontal forces add up to zero, because here's the easiest way to think about it. If I want to figure out how much total force is going left, all I have to do is look at the silhouette from the left side. And that's the area I'm going to use to find the force to the left. I want to find the force to the right, I look at the silhouette from the right side. That's going to be the area for the force to the right. But how's the silhouette from the left compared to the silhouette from the right? Yeah, they're the same. So that means you're always going to have the same forces for the horizontal because the pressure is the same for the same depth. But not so for the vertical because you have a different pressure on the top than on the bottom. So the vertical forces are the only two that are shown on that block from the water pressure. The addition on the figure to the right is I didn't put the force of gravity on the block. I just put the forces of the water. I only want to find the buoyant force for my first calculation, so I only put the forces acting by the water. So if I look at that, my force change to something that's permanent. Force buoyant is going to be equal to, and let's take the one on bottom, so the pressure on the bottom multiplied by the area of the bottom minus the pressure on the top multiplied by the area of the top. Well, since this is a cylinder, those two areas are the same. I've now gone from general to specific when I've said the areas are the same. The calculation I'm going to do turns out to be generally true, but I'm doing it for a specific case. So I'm going to factor out that area, and I'm just going to call it area now because it's the same area on top and bottom. But we've already learned what the pressure difference is. Delta P is equal to pressure bottom minus pressure top is equal to the density of the fluid times G times the height. And so I'm going to substitute that in there for the pressure difference. The force buoyant is equal to density of the fluid, GH, times the area. Now, once again, I just said I'm doing a specific case, but it turns out to be generally true. What is height times area for my cylinder? Volume. And so this is equal to density of the fluid times G times the volume. And I'm going to put here a subscript displaced. That is our equation for the buoyant force. The buoyant force is the density of the fluid times the acceleration of gravity times the volume that was displaced. So in this problem here, the volume displaced was the area times the height of my object. I know it said D there. So that's my buoyant force. Question, Mahala?
Isn't the area multiplied by everything in the brackets? Or is it
Yes, it is. It is, but I can just take H times A as V. It's still multiplied by everything. So this is our equation for buoyant force. If any problem ever asks you what's the buoyant force, this is a correct equation. Question,
If we're dealing with an object that is in a cylinder, like maybe a cone with two different areas on top and bottom, do we just keep it the same and then calculate with those separate areas?
This equation here is generally true. That is,
Okay.
when I say generally true, it means in all situations. That I know sometimes it's like usually is what you mean by generally, but when physics, generally true means it's true in all situations. So you just use this equation, you calculate what the volume is of the cone. So the question, that may not have been heard in Southwestern, the question is, what if the shape is not a cylinder? What if it's something like a cone? What do I do then? And the answer is you simply take the volume of the cone, so you calculate that volume and put it into this equation. So that's the buoyant force. Now if we look back at this water, the thing that was displacing water, in this case it's shown as water, but I said it could be anything. So like in lab, it could be a piece of zinc. And so I'm going to have the force of gravity on that object. I'm going to change color for this. Force of gravity on the object is equal to, and what's the general go-to equation for the force of gravity on the object? The mass times gravity. Well, I'm going to take this and I'm going to put it in terms of the volume of the object. So how do I go from mass of the object to the volume of the object? I use the density. We know that density of the object is the mass of the object divided by the volume of the object. So that means the mass of the object is density times volume. So this is density of the object times G times volume of the object. Now you look at that second equation and you can see probably why I did it. I did it because it looks similar. The difference is the buoyant force was the volume displaced. The force of gravity was the volume of the object. And of course the density was the density of the fluid or the density of the object. So now we look at this and we can actually make a quick calculation of, does the object float or does the object sink? So let's start with an object that sinks. If an object sinks, a sinker, what would you tell me about the volume displaced? If I put a piece of, let's say it's iron, in water and it sinks to the bottom, how does the volume displaced relate to the volume of the object? They're equal. So if it sinks, the volume displaced is equal to the volume of the object. And which force is going to have to be bigger if it sinks? The force of gravity or the buoyant force? Okay, force of gravity. So you have two conditions. The volume displaced is equal to the volume of the object, and force of gravity in the object has to be greater than the force buoyant. So let's put those two together to see what that tells us about things that sink. So we're going to have the force of gravity in the object, density of the object, times G times volume of the object must be greater than the force of buoyancy, density of the fluid, times G times volume displaced. But volume displaced is equal to volume of the object. So that means I can cancel the G. I meant to change color there. Cancel the G's and cancel the volume, since displaced and object are the same if it sinks. And so this gives me a condition. If the density of the object is bigger than the density of the fluid, it will sink. Now, you probably all knew that before I ever started this, right? More dense things sink, less dense things float. But now we've shown mathematically why. So that was a sinker. What about a floater? If things float, how do the volumes compare?
Displaced is less than the volume of the object.
Yeah, the displaced is going to have to be less than the volume of the object if it floats. What about the forces, the force of gravity and the force of, I'm actually going to put this on the bottom of the next slide. So for a floater, volume displaced is less than the volume of the object. What about the forces? Was that you answer, Mahal? No? I couldn't hear. Okay, what was it, Maranatha? In this case, no. If it floats, it needs to be in equilibrium. So that means that the upward and downward floats have to be equal. So that means the force buoyant needs to be equal to the force of gravity in the object. So now I'll say, well, actually, I don't really need to go any further. That's all I really need to do. The volume that is displaced, I can calculate by taking force buoyant, density of fluid, times G times volume displaced, is equal to the force of the object, density of the object, times G times volume of the object. And, of course, cancel out the G's. And now I have a relationship that says volume displaced is equal to volume of the object times density of the object divided by density of the fluid. And so I can calculate how much volume is displaced if I know the densities, or I can calculate the density of one if I knew the density of the other and the volume displaced. You had a question, Jordan?
Yeah. So would it be possible for the force of buoyant to be greater than the force of gravity? What would we call that?
Okay, it would be possible. Let us say, since you, I know, are a scuba diver, let us say that you are down low and you fill up an air bladder with air from your tank. Suddenly, your buoyant force becomes larger than your force of gravity. Why? Because you have increased the displacement without changing the mass at all, since you just moved air from the tank into the bladder. So you increase the displacement, you increase the buoyant force, so you have a net upward force because the buoyant force is bigger than gravity, and you start floating upward because you have a net upward force.
So what would we call that then?
Well, we would call that floating to the surface.
Okay.
But it's not an equilibrium. Just like if something is sinking before it hits the bottom, it's not in equilibrium, it's sinking. Actually, it could reach equilibrium pretty quickly because terminal velocity comes quickly, but ignore that. Okay, so the net force acting on the object due to the fluid is what we call the buoyant force. And what Archimedes figured out with his whole bath thing was that the weight of the fluid displaced is equal to the buoyant force. Why? Well, if we have, I actually have to go back to this one. If we have the force buoyant is equal to the force of gravity. Now, his equation it's true in all cases, but let's take the case for a sinker. If we have the force buoyant is density of the fluid, G times volume displaced, force of the object is density of the object, G times the volume of the object. We set these equal, and what we find is that the buoyant force has the weight. That is the weight, right? Mass times volume is, or density times volume is mass times G. It's the weight of the fluid that was displaced. If it's floating, these equations are still correct. The volume displaced is less because you displace less water, but it's still the mass of the water displaced is the fluid density multiplied by volume displaced. So what he realized was it's always going to be that the buoyant force is equal to the weight of the displaced fluid. And so that's how he was able to then go forward with his work. And just to make sure we got that, any shape this is correct for. This was not specific to my cylinder. It could have been a cube, it could have been a star, I don't care. It's still going to be the same relationship. So second and third clicker questions. Which condition is true only when an object floats? Now notice it's only when. Not which is true, but which is true only when. Okay, about 5 more seconds. All right, let's see what we got. Okay, we did not have universal agreement. It's not stopping like it's supposed to. It was 25, 26, and this number was a small number. It disappeared rather than a, okay, there we go, 5. So we don't have good agreement here. So this is one where I'm going to turn it to you discussing it with people next to you. Talk to the people next to you about which one you believe to be true only when an object floats.
I know we
Honestly, it is because Newton's second lowest. It's easy stuff like the last one was assignment. 5 minutes.
I know, I did it so fast.
Yeah.
Okay, let's go ahead and answer this again. See if we get a better or a worse distribution. Yes, we're doing it again. Okay, give it about 5 more seconds here. Okay, this time we had a much smaller spread, 11 and 44. And now we're going to go to Thomas, who I saw explain to the person next to him. Thomas, what was your answer and your reasoning?
I chose B because A is when the object is underwater, and B is the force, the buoyant force is equal to the weight. Because I did concept coach and I saw a picture of it.
Okay, so concept coach was his key. Okay, thank you. Looking at these answers, B was indeed the correct answer. The buoyant force is equal to the weight of the object if it floats. If it sank, the buoyant force was less. Part A, or answer A, this one is always true. Not if it floats, not if it sinks, but always. So that's what we're going to be looking at in our lab because it's always true. So it makes it an easy measurement to make. The buoyant force is 0. Well, that was a poor choice, which thankfully nobody answered after the second time around. Okay, our second question about this. What condition leads to floating? Sorry, you can answer starting now. So what condition leads to floating? 2 have to do with density, 2 have to do with mass, 2 have to do with volume. Only one is correct. Actually, I suppose somebody could point out that there's... Okay. We have a pretty strong agreement here. And the person whose card came up is again over there at Southwestern, Ulana Nwachukwu. And if I say it wrong, you can correct me.
I chose B.
Chose B, and what was your reasoning? Because it made more sense. Okay, and it does make more sense. It's the correct answer. We worked it out that if you have it floating, then you're going to have the fluid is more dense, the object is less dense. Because, and remember, we worked it out. It's the easiest to actually go and point to the equation. If it's floating, we had that equation. The volume displaced is less than the volume of the object. And if you take the equations for the forces being equal, you find that you're going to have the volume, or well, in terms of the densities, since the volume displaced is less than the volume of the object, then that means density of the object has to be less than the density of the fluid from this equation right here. Okay, now for clicker questions, One more thing on this before I once again change areas. The term specific gravity. Specific gravity is simply a term that makes it so we don't have to have units with density. Specific gravity means the density of whatever you're talking about divided by the density of water pure water at 3.98 degrees Celsius in 1 atmosphere. Why so specific? Because the density of pure water at 1 atmosphere at a temperature of 3.98 degrees Celsius is 1,000 kilograms per meter cubed. So if somebody says this material has a specific gravity of 3.25, all that means is it has a density equal to 3.25 times 10 to the third kilograms per meter cubed. It's just a way of not having to say the units. So that's another term for specific gravity, just so when it comes up, we know what it refers to. It's just telling us the density once again. So let's do a problem that has to do with buoyancy. So the problem here, it's a pretty drawn out problem. A small statue in the shape of a falcon. Oh, crud. I had this problem for the last class, and I actually had a picture of the Maltese falcon, replica, since obviously it's not a true story, to go with it. So we have a falcon that has a weight of 24.1 newtons. The owner of the statue claims it is made of solid gold. The density of gold is 19.31 grams per centimeter cubed. Gold is very dense, much more dense than lead. Not as dense as osmium, but it's a very dense material. When the statue is completely submerged in the container that's brimful of water, the weight of water that spills over the top into the bucket is 1.25 newtons. So that tells us, well, what does that tell us? Okay, it tells us the buoyant force, if it's completely submerged, which it will be if it's made out of gold, is 1.25 newtons. Find the density and specific gravity of the metal. If you find the density, you found the specific gravity, right? Because those are just units. Is the density consistent with the claim that the falcon is solid gold? So we're doing a test here, much like the test that Archimedes did, much like what we're going to do in lab tomorrow. So I have my object. Here's my Maltese falcon. Not nearly as pretty as what I had before. Force of gravity is equal to 25.1 or 24.1, excuse me. And then we have when it's submerged. So here's my tank of water. And when it's submerged in this water, the fluid that runs over, the force of gravity displaced is equal to 1.25 newtons. Now I can actually go to what we did before, but I'm going to start with the beginning. It sank, right? So because it sank, I know that the volume displaced is equal to the volume of the object. And furthermore, I know the force buoyant, which is equal to the density of the fluid times G times the volume displaced, is equal to 1.25 newtons. Whereas the force of the object is equal to density of the object times G times the volume of the object is equal to 24.1 newtons. Now I'm going to take these two equations as I've written them, and I want to solve this for the density of the object. So the easiest way to solve this for the density of the object is to change the order and divide. So I'm just going to take these two equations and divide. And so if I divide, notice I have some things that will cancel. G will cancel. And because it sank, the volume object is equal to the volume displaced, so those cancel. And I'm left with density of the object is equal to density of the fluid times 24.1 newtons divided by 1.25 newtons. So, someone with the calculator, would you kindly calculate what 24.1 divided by 1.25 is?
19.28.
19.28. Okay, so it's 19.28 times density of the fluid. What fluid did I put this in? Water. So what was the density of the fluid? 1,000 kilograms per meter cubed. So I can immediately say the specific gravity is equal to that 19.28, and the density of the object is equal to 19.28 times 10 to the third kilograms per meter cubed. So now I just look back and say, does that match? 19.31 grams per centimeter cubed is supposed to be the density of gold. Well, that's different units, right? Grams per centimeter cubed. So let's go through a quick unit conversion. If I'm going to convert that, I'm going to need to multiply it by, first, converting to kilograms. So I want to cancel the grams, which means I'm going to have grams on bottom and kilograms on top. And of course, 1 kilogram is 1,000 grams. And then I have centimeters cubed to meters cubed. So centimeters is on bottom, so I'm going to put centimeters on top, meters on bottom. And there's still one thing I have to do. What is missing from this? A lot of people think you're done at this point, but you're not. I have to cube this because it was centimeters cubed. If I just did the centimeters per meter, I'd be left with units of grams per centimeter squared times meter, which would be useless. So if you put this together, 100 cubed is a million. A million divided by 1,000 is 1,000. So that means this is equal to 19.31 times 10 to the third kilograms per meter cubed. So we compare 19.31 and 19.28. To within our significant digits, how many significant digits did I have in my mass, my weights? 3. So to within 3 significant digits, those are the same number. So I'd have to say within the precision of my measurements, I cannot say that this is anything but pure gold. Okay, next is how do we determine the density of water? Now you guys are all young. You never had to check the density of fluid in your car's battery, right? Never had to do that. But that's something we had to do when I was a child. You had to put fluid in your battery, and you had to check to make sure that your battery fluid had appropriate density. So this is how we measure density. Put water in here, and then I'm going to take an object that's hollow, has some lead down here in the bottom, and has a piece of paper where somebody has actually said, okay, if it floats with the water level at this height, it's a density of this. And so I just put this in here. There's a certain weight to this thing, and so it's going to displace an amount of water equal in weight to the weight of that object. And then by measuring the height of the water, I can determine the density. So this shows that it has a density of right at 1.000 grams per centimeter cubed, which is what it should be if it's water, right? So I can measure the density. If I replace this with some other kind of fluid, like let's say I replace it with ethanol. Ethanol has a lower density than water, and so this should float higher because of the lower density of the ethanol. Higher?
I mean lower.
Lower, yeah. I'm good at this game. This here is a homemade one. It's just a piece of wood with some copper wire wrapped around it and a grid. And you could take this and obviously I need to have a little more water to actually make this work, but I can use that grid and just calibrate if I use different fluids to make my own water density meter known as a hydrometer. So they simply work by displacing water. Now let's talk about ships. What floats a boat? What? You put that water that boat in water. What are boats traditionally made out of? Okay, wood or steel. Wood, depending on the kind of wood, it may float or it may not. Some woods are more dense. Those woods don't float. Some are less dense, they do float. So it depends on what you make it out of, if it would float or not. Iron or steel, well, that definitely does not float. And yet we have these boats that float. What's the key that allows a boat to float? It's hollow, so the water that it's displacing is a much bigger volume than the actual volume of the metal. Now, when I was a kid growing up in Monterey Bay Academy, on Sabbath afternoons, we would take walks up to the cement ship. The Navy made a ship out of concrete, and they were sailing it down the California coast when a storm came. So it cruised on into the Monterey Bay to seek refuge during the storm, but it was run aground and did, unfortunately, what concrete does. It broke. And so there it sits, this broken ship. So the government gave up on the idea of making concrete ships when they realized these things are just too fragile, too brittle. But their idea was to try to find something that was a little less dense than steel, I think. Okay, before I start with menisci for plural, I have my leaking display here. Come on, baby. Try to get the bubbles out. So let me put a little more food coloring in the one that you can't see. So I have just water with food coloring in these. And if you look at the heights of the water levels, how do the heights of the water levels compare? They're pretty much the same. They're pretty much the same because of Pascal's principle. Pascal's principle says at the same height, we should have the same pressure in any fluid. And then as we go up, we know the pressure difference is equal to the density of the fluid times G times just the change in elevation. So we get up to a certain elevation and we should be down to atmospheric pressure. So they should all be the same height. But if you get real careful in your checking, you actually see that this one is a little bit higher than this one. Why would the smaller gauge be slightly higher than the bigger gauge, the bigger hole? Because of what? Okay, this is where we have adhesive and cohesive forces coming into play. And the term that in general is called capillarity. So water has a situation where the cohesive force is less than the adhesion to water. What that means is water molecules have a certain force that holds them together. Right? They're in a liquid stage. They can't break free of the water. There's a force you can also talk about as energy, so we call this either the surface force or the surface energy, surface tension, or the surface energy. But there's a force that holds the water molecules together. But the water molecules are also attracted to glass, and there's a force that attracts the water molecules to glass. And the water molecules are attracted to glass more than they're attracted to water, which means that the water molecules actually have lower energy when touching glass than when touching other water molecules. As a result, you'll have the water climb up the sides because it's lower energy to go up in elevation but touch glass. And so that leads to what we call a meniscus, which is that general shape of going like this in the water. And because it's being pulled up on the sides, the actual water level will be pulled up a little. If the tube is smaller, then the weight that's in a certain height is smaller, and you'll pull the water level higher. So you have more capillarity, a higher draw up from the glass tube if it's a smaller glass tube. Now, if we go from water to the mercury, so over here, mercury, it's just the opposite. Mercury has a stronger force between mercury atoms, the cohesive force, than the adhesion between the mercury and the glass. So it actually tries to pull away from the glass so it can touch more mercury because that's a lower energy state. And that caused it to have a depressed instead of going up capillarity. Okay, we are out of time, so I'm going to stop right. Actually, here's a figure. I'll go to the clicker question on this, and then we'll leave after the clicker question. So here's where you can see it climbs higher in a smaller diameter. So for our last question, why is capillarity more obvious in a smaller tube? Go, Gila. You're still not here. Okay. We had the answers were not in the right ballpark. The cohesive and adhesive forces aren't affected by changing the size, but it's the weight of the fluid in the tube that changes. When you make a smaller tube, the weight in the tube is smaller, and so it's allowed to push higher or lower. Okay, have a great day. I'll see you for